Sometimes I wonder where you are listening to these lines. In a quiet, dark room, on a slow night train rolling along the tracks, or curled up on a sofa with a warm cup of tea. Wherever you are, as long as you feel comfortable and safe, that is enough. Tonight, we'll step together into a region of science that is both beautiful and strange, the world of quantum physics. If gentle journeys like this one are something you enjoy, a like or a subscription will help this small channel keep drifting calmly through the vast sea of algorithms. And to those who have been here for a while, I'm truly grateful. There is only one small risk. Tonight's topic might be a little too interesting, but if you happen to lose sleep, at least you'll understand a bit more about why particles sometimes behave like waves, and why reality seems to make up its mind only when someone observes it. In everyday life, the world appears very certain. If a cup falls, it falls. Toss a coin and it lands. Close your eyes, and the moon is still there. But at the beginning of the 20th century, when scientists began looking deeper into the structure of matter, that familiar picture started to tremble. At extremely small scales, light suddenly stopped being simple. It could be a wave, but it could also be a particle. Particles of matter, it turned out, could sometimes exist in multiple places at once until a measurement was made. And even more strangely, observation didn't just reveal something that was already there, it seemed to change the very phenomenon being observed. These results were not experimental errors or poorly calibrated instruments. They appeared again and again, and they shook the foundations of classical laws that had stood firm for centuries. From that point on, a new view of reality began to emerge, one where certainty gives way to probability, and cause and effect do not always unfold in the familiar order we expect. But this story does not begin with strange paradoxes. It begins with a problem that seemed surprisingly simple. Let's go back to the early 20th century. At that time, physics appeared almost complete. The laws of motion were well understood, thermodynamics worked neatly, and light was well explained within the framework of electromagnetism. Many scientists even believed that the great questions of the universe had already been answered. Only a few small details remained to be swept up, like bits of dust left in the corner of a room. One of those specks of dust involved a familiar phenomenon. What happens when an object is heated? Imagine a piece of metal placed in a fire. At first it glows red, then gradually turns orange, and eventually white-hot as the temperature rises. That light is called blackbody radiation, the electromagnetic radiation emitted by any heated object. This phenomenon is easy to observe, so it seemed reasonable to think that explaining it would also be simple. But when physicists tried to describe it using classical equations, things began to turn absurd. The formulas predicted that as temperature increased, an object would emit more and more energy at shorter wavelengths, especially in the ultraviolet region. And if you followed that logic to its conclusion, the energy at higher frequencies would keep increasing all the way to infinity. The result was so unreasonable that it earned a dramatic name: the ultraviolet catastrophe. No adjustment within classical physics could rescue these equations. The mathematics kept sliding into nonsense, while experiments showed something entirely different. Clearly, within the scientific picture of the time, a crucial piece was missing. And then, a German physicist entered the story. Max Planck was not the kind of scientist who enjoyed breaking rules. He was careful, even somewhat conservative, and deeply trusted the foundations of classical physics. But faced with the blackbody radiation problem, he decided to try a bold idea, even though he himself did not fully believe it. He proposed a simple but strange hypothesis. Perhaps energy cannot be emitted in just any arbitrary amount. Perhaps it comes only in small, discrete packets, like coins that cannot be cut in half. He called these smallest packets of energy quanta. This idea completely contradicted the classical view of energy as a smooth, continuous flow. According to the new idea, energy does not glide smoothly, it jumps in tiny steps, depending on the frequency of the radiation. Planck even introduced an extremely small number into his equation to describe the size of these energy packets. Today, we call it the Planck constant, and when he inserted that assumption into the equations, something remarkable happened. The ultraviolet catastrophe disappeared. The mathematical predictions suddenly matched the experimental results perfectly. Planck had solved the problem, but he himself remained hesitant. In his eyes at the time, the idea of energy packets was merely a clever mathematical trick to make the numbers work, not necessarily the true way the universe operated. Interestingly, Max Planck, the man who laid the foundations of quantum physics, did not believe he had uncovered a profound truth about the universe. To him, the idea of energy packets was merely a temporary solution, an elegant trick to persuade the equations to stop disagreeing with reality. Planck believed that sooner or later someone would find a better explanation, one that did not require the strange assumption that energy must appear in small, discrete pieces. But the history of science has its own way of playing with such modesty. The very hypothesis Planck regarded as a mathematical convenience became the first stone in an entirely new theoretical structure, quantum theory. The paper he published in 1900 did not look like a revolution. There were no grand declarations, no claims that the foundations of physics were about to change. There was only an extremely small constant, a different way of thinking about energy, and a solution to the blackbody radiation problem that had puzzled scientists. Yet from that moment on, the feeling that physics was nearly complete slowly began to fade. At the beginning of the 20th century, light seemed to be well understood. Thanks to the equations of James Clerk Maxwell, scientists knew that light was a form of electromagnetic wave propagating through space. It reflects from mirrors, refracts when passing through water or glass, bends around narrow openings, and produces intricate interference patterns. All of these behaviors fit perfectly within the wave model. So after Planck's quantum idea, most physicists believed that with a few minor adjustments, the old picture would remain intact. But an experiment that seemed quite simple began to shake that confidence. When light shines on a metal surface, electrons can be knocked out of the material. This phenomenon is called the photoelectric effect. According to classical understanding, this made perfect sense. Light carries energy. The energy is transferred to the electrons, and they are pushed out of the metal. If the light becomes brighter, meaning the wave is stronger, then the electrons should receive more energy. Yet experiments showed something completely different. The brightness of the light was not the deciding factor. What mattered instead was the frequency of the light. If the light's frequency was below a certain threshold, no electrons would be released, no matter how intense the light was. But once the frequency passed that threshold, even a weak beam of light could knock electrons out of the metal. The difference was clear and decisive, so clear that it could not be explained by the conventional wave theory. In 1905, Albert Einstein proposed a solution to this mystery. He suggested that light sometimes behaves not like a wave, but like tiny packets of energy traveling through space. Each of these packets carries a specific amount of energy directly determined by the frequency of the light. Einstein called them light quanta, later known by the more familiar name, photons. If a photon carries enough energy, it can knock an electron off the surface of a metal. If it does not, then no number of photons will be able to do so. This idea extended directly from Planck's work, but Einstein went one important step further. He did not see energy packets as a mathematical trick. He believed they were the true nature of light itself. From that point on, a strange concept began to emerge in modern physics. Light is both a wave and a particle. Depending on how we observe and measure it, it can display either of these two natures, a peculiar characteristic that seems to be an inseparable part of nature. If we zoom into the world of light closely enough, the familiar image of a smooth wave begins to dissolve. In its place, we start to see tiny packets of energy photons, each carrying its own amount of energy depending on its frequency, colliding with atoms and altering the world, one interaction at a time. From this point, a strange idea emerges in physics. Light is both a wave and a particle. What makes this concept confusing is not that it is too complex, but that it breaks the categories we are used to. In classical physics, something must be either a wave or a particle, but never both at the same time. Yet the quantum world seems unconcerned with such boundaries. Einstein's explanation of the photoelectric effect made this clear. Each photon carries an amount of energy directly proportional to the frequency of the light, just as Planck had originally suggested. This explains why light with a low frequency, no matter how intense it is, cannot knock electrons out of a metal. Each individual photon simply does not carry enough energy. The impact of this idea was so profound that in 1921, Einstein received the Nobel Prize in Physics for this work, not for relativity, as many people assume. Even so, Einstein himself felt uneasy about the probabilistic implications of quantum mechanics. He famously remarked that God does not play dice with the universe, but whether we like it or not, the rules of nature seem to be changing. Light, the very thing that illuminates the world around us, refused to fit neatly into any conceptual box. It spreads like a wave, collides like a particle, and exists as discrete packets of energy. From a simple experiment involving metal and light, the foundations of physics had begun to tremble. And then another experiment, even simpler, pushed the story further. Imagine a table, a flashlight, and a piece of cardboard with two narrow slits cut into it. When light passes through those two slits and strikes a screen behind them, we see alternating bands of light and dark, a familiar interference pattern of waves. This fits perfectly with the wave model of light. As waves pass through the slits, they spread out and overlap. Where the crests of the waves meet, the light becomes brighter. Where they cancel each other out, darkness appears. Everything seems neat and understandable, but when scientists reduce the intensity of the light so that only individual photons travel toward the slits, the story begins to grow strange. Each photon arrives at the screen as a tiny point of impact. Yet, after many such impacts, those points do not form two bright lines behind the slits, as we would expect from particles. Instead, they gradually build the very interference pattern associated with waves. This means that each photon seems to have interfered with itself. Does the photon pass through both slits at the same time, or does it exist as a spreading wave before it reaches the screen? These questions made physicists even more curious. They decided to place detectors at the slits to observe which slit the photon actually passed through. And when they did so, something remarkable happened. The moment the detectors were turned on, the interference pattern vanished. The photons began to behave like ordinary particles. Each photon passed through only one slit, and the screen showed only two distinct regions of impact. When the detectors were turned off, the interference pattern returned. Turn them on, and it disappeared. Turn them off, and it came back again. It seemed that the mere act of observation was enough to change the photon's behavior. The double-slit experiment has been repeated countless times with photons, electrons, and even large molecules composed of hundreds of atoms. The result is always the same. When unobserved, particles display wave-like behavior and interfere with themselves. When observed, they behave like distinct particles. This suggests that at very small scales, particles do not travel along a single, definite path. Instead, they exist as a collection of possibilities, a cloud of potential outcomes. Only when a measurement is made does one of those possibilities become reality. Physicists have proposed many interpretations of this phenomenon. Some describe it using the probabilistic language of the wave function. Others imagine that each possibility branches into its own universe in the many worlds interpretation. But regardless of which interpretation one prefers, experiments continue to tell the same story. Before it is observed, a particle does not seem to have decided its state. From a flashlight, two narrow slits, and a screen, we have touched one of nature's deepest mysteries. At its most fundamental level, the universe does not resemble a clockwork machine driven by rigid gears. It looks more like a tapestry woven from countless possibilities, and the way we observe it appears to be part of the story. While these questions continued to puzzle scientists, in the 1920s a new mathematical tool began to emerge to describe this strange world. It was called the Schrödinger equation, a formula that is not merely symbols on a blackboard, but almost like the quiet heartbeat of quantum mechanics itself. As physicists tried to understand particles that behaved like waves and probabilities at the same time, Newton's familiar laws of motion gradually proved insufficient, and so, an entirely new mathematical language began to take shape. When physicists began to realize that the tiny particles of the microscopic world no longer behaved like little marbles, they understood that the old laws were no longer sufficient. The universe seemed to be demanding an entirely different language to describe it, and in 1926, Erwin Schrödinger introduced that language. He wrote down a new equation, elegant, compact, yet immensely powerful, that did not merely describe the motion of particles, but also how their quantum states evolve over time. At the center of that equation lies a concept with a rather mysterious name, the wave function, usually represented by the Greek letter psi. If that sounds abstract, think of it in a simpler way. The wave function is like a probability map for a particle. It does not say exactly where the particle is. Instead, it quietly tells us where the particle is more likely to appear. In classical physics, an object always has a definite position and velocity. We can draw an arrow pointing precisely to where it is and how fast it is moving. But in Schrödinger's world, a particle is not a clearly defined point. It is more like a rippling cloud spread through space, containing many different possibilities for its position. The Schrödinger equation allows physicists to track how this cloud of possibilities changes over time. When a particle moves, what actually changes is not just its position, but the entire distribution of all the possible outcomes. Only when we perform a measurement, when we directly ask, "Where is the particle?" does that cloud of probability collapse into a single point. Suddenly, all other possibilities disappear, leaving only one answer, but only after we look. This perspective is very different from the familiar mechanical picture that dominated science for centuries. Instead of clear trajectories like planets orbiting the sun, quantum mechanics presents a universe woven from hazy probability fields, where certainty appears only at the moment of observation. Strange as it may sound, Schrödinger's equation works astonishingly well. Physicists have used it to explain the structure of atoms, the way molecules bond together, the behavior of semiconductors in microchips, and even phenomena such as superconductivity. It also predicts remarkable effects like quantum tunneling, where a particle can pass through a barrier that classical intuition says it should not be able to cross. One of the most striking successes of this equation is its explanation of the structure of the hydrogen atom. Before quantum mechanics, scientists could not understand why electrons orbiting the nucleus remained stable instead of collapsing into it. Schrödinger showed that electrons do not orbit the nucleus like planets. Instead, they exist as standing wave patterns around the nucleus, forming regions of probability known as orbitals, those soft, cloud-like shapes often shown in textbooks. Even so, Schrödinger himself was not entirely comfortable with the philosophical implications of the theory. He famously proposed a thought experiment involving a cat that is both alive and dead at the same time, meant to illustrate the strange idea that quantum states can exist simultaneously until they are observed. These ideas gradually led to another principle, also born in the 1920s and destined to become one of the pillars of quantum mechanics. Werner Heisenberg called it the uncertainty principle. This principle states that there is a fundamental limit to how much we can know about the microscopic world. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not because our measuring instruments are still crude. Even with perfect technology, the uncertainty would remain. Part of the reason is that to observe a particle like an electron, we must shine light on it, and each photon of light that collides with the electron inevitably alters its motion. But more deeply, the reason lies in the very wave-like nature of particles. A wave in the ocean can stretch across the surface of the water. We may point to where the crest appears, but the wave itself is not a single point. The same is true for an electron. It exists as a spread-out wave function. If the wave function is widely spread, the electron's position becomes uncertain, but its momentum can be determined more clearly. On the other hand, When we try to compress the wave function to determine the position precisely, the uncertainty in momentum grows. It is a fundamental trade-off written into the fabric of the universe, a limit imposed by nature itself. And in the quantum world, there is no way to avoid it. At the heart of the uncertainty principle lies a simple yet profound mathematical relationship. The product of the uncertainty in a particle's position and the uncertainty in its momentum must always be greater than or equal to an extremely tiny number, Planck's constant, divided by 4 pi. This number is so small that in the familiar world around us, its effects are almost impossible to notice. You can measure the position and speed of a baseball with astonishing precision without ever approaching the quantum limit. But when we descend to the scale of electrons or atoms, that uncertainty becomes impossible to ignore. It is not merely a small detail in an equation, it becomes a fundamental part of how the world operates. If we try to confine a particle within an extremely small space to determine its position precisely, its momentum immediately becomes more uncertain. The particle begins to move erratically, as if resisting the attempt to pin it down. The more we try to fix it at a point, the greater the uncertainty becomes. It feels a bit like trying to hold a handful of mist in your palm. The tighter you squeeze, the more it slips away. Loosen your grip slightly, and the vapor gathers again. The uncertainty principle acts like a warning label attached to the quantum world, reminding us that our knowledge has limits not because humans lack ability, but because reality itself is built that way. In fact, this very principle also explains something that might seem quite simple: why electrons do not fall straight into the nucleus of an atom. If an electron were to remain perfectly still inside the nucleus, its position would be known with complete precision. According to the uncertainty principle, that would mean its momentum becomes infinite, requiring infinite energy. Nature does not allow such a thing to occur. As a result, the electron cannot simply sit still at a point. Instead, it exists in regions of probability around the nucleus, hovering in a state sustained by the very rules of quantum mechanics. Interestingly, this uncertainty is not chaos. It is not meaningless randomness. Rather, it resembles a delicate haze spread across reality, a kind of structured ambiguity. Because of it, particles can tunnel through barriers that would otherwise seem impossible to cross. Atoms can remain stable, and chemical reactions can occur. If the universe were completely rigid and perfectly deterministic, the complex structure of matter and life itself might never have emerged. And then, from that hazy region of probability, an even stranger idea appears: quantum superposition. In everyday life, everything seems to settle into a clear state. A coin is either heads or tails. A light switch is either on or off. But at the quantum level, small physical systems sometimes do not choose a single state immediately. Instead, they exist in a combination of multiple possibilities at once. Imagine a quantum coin. When it is tossed, it does not secretly land on one side while we simply have not looked yet. Instead, it genuinely exists in a state of both heads and tails at the same time. Only when we observe it does that superposition collapse into a definite outcome. Before the moment of observation, the result is not merely unknown, it is multiple possibilities existing simultaneously. This idea led to one of the most famous images in physics: Schrödinger's cat. In that thought experiment, a cat is placed inside a sealed box along with a radioactive atom and a mechanism that releases poison if the atom decays. If the atom decays, the poison is released and the cat dies. If it does not, the cat remains alive. Because the atom can exist in a superposition between decayed and not decayed, the cat, according to quantum logic, is also both alive and dead until the box is opened. Schrödinger proposed this example not to claim that such a thing truly happens to cats, but to highlight the strangeness of applying quantum rules to the larger world. Despite how bizarre it sounds, superposition is not a flaw in the theory. On the contrary, it is one of the most powerful features of quantum mechanics. Modern quantum technologies are being built directly upon this principle. In classical computers, information is stored in bits, Each bit can only be either 0 or 1. But in quantum computers, the basic unit is the qubit, and a qubit can exist simultaneously in states 0 and 1 thanks to superposition. When many qubits become linked together, they can represent an enormous number of states at once, allowing certain complex problems to be solved far faster than with ordinary computers. Superposition also appears in quantum cryptography, where it helps detect any attempt to eavesdrop on information, and in extremely sensitive sensors capable of measuring tiny changes in magnetic or gravitational fields. Yet quantum states are extraordinarily fragile. Even a small interaction with the environment, a stray photon, a vibration, or even a single air molecule can destroy the superposition. This phenomenon is known as decoherence, and it remains one of the greatest challenges scientists face when trying to build stable quantum systems. Quantum superposition is beautiful, yet strangely fragile. Even the slightest interaction with the outside world, a stray photon, a faint vibration, or even a single air molecule can cause it to collapse. Keeping a quantum system in superposition is like trying to balance a feather on the tip of a pencil while someone sneezes in the next room. The smallest disturbance can instantly destroy the balance. That is why quantum systems reveal their full power only when they are extremely well isolated from their surrounding environment. They open a doorway to a world of probabilities rather than certainties, and they force us to rethink what it truly means to say that something exists. From here emerges a deeper question. Is the quantum state itself reality, or merely a representation of what we know? Some physicists argue that the wave function is simply the best way to describe our knowledge of a system until a measurement is made. Others believe that the wave function is a real part of the physical world, and that particles genuinely exist in multiple states at once, until measurement forces them to choose. Whichever interpretation turns out to be correct, quantum superposition compels us to loosen the familiar boundaries of classical logic. In this world, a system can be both here and there, both this and that, until observation pulls one possibility from the intricate tapestry of many. From superposition arises an even stranger phenomenon: quantum entanglement. To understand it, we can begin with a familiar example. Imagine two gloves, one left-handed and one right-handed, placed into separate boxes and sent to two distant locations. When you open one box and see the left glove, you instantly know the other must be the right glove. There is nothing mysterious about that. The gloves were already different from the start. But entangled particles are not like gloves that were pre-packaged that way. They are more like two gloves that have not yet decided whether they are left or right until one of the boxes is opened. When two particles interact in certain ways created together, colliding, or becoming linked within the same system, their quantum states can become tightly connected. From that moment on, measuring one particle immediately determines the state of the other, no matter how far apart they are. Imagine two entangled photons with undefined polarization. They exist in a shared state containing all possibilities. But when one photon is measured and found to have polarization in a particular direction, the other photon instantly takes on the corresponding polarization. No signal travels between them, and there is no delay. The two outcomes appear simultaneously, as if the universe has updated both at once. It was precisely this phenomenon that led Einstein to famously call it spooky action at a distance. He did not like the idea at all. In Einstein's view of the world, events in one place could not instantly influence events somewhere else without a signal traveling between them, and nothing could move faster than light. So in 1935, Einstein, along with Boris Podolsky and Nathan Rosen, proposed that quantum mechanics might be incomplete. They suggested that there must exist some kind of hidden variables determining the outcomes in advance. But decades later, experiments began to test that idea directly. The physicist John Bell formulated a mathematical inequality that could distinguish between hidden variable theories and the predictions of quantum mechanics. When experiments were carried out again and again, the results consistently supported quantum mechanics. Entangled particles truly behave in ways that local hidden variables cannot explain. That does not mean we can use quantum entanglement to send messages faster than light. The result of each measurement is still completely random, so no controllable information can be transmitted. But the correlation between the particles is real. Whether separated by a room, a continent, or even the distance between stars, quantum entanglement remains. Modern experiments have even created entangled particles separated by hundreds of kilometers using satellites. What continues to intrigue physicists is the true nature of this connection. Is entanglement an invisible thread linking particles together, or is it a form of information spread between them? Some theories even suggest that space-time itself might emerge from a network of entanglement among tiny quantum systems. If that is the case, then entanglement would not simply occur within space, it might actually be what allows space to exist. Whatever the ultimate explanation, this phenomenon has moved beyond philosophy. It is becoming the foundation of new technologies, transferring quantum states between systems through quantum teleportation, securing information with quantum cryptography, and powering the computational potential of quantum computers. What once troubled Einstein has now become one of the most powerful tools of modern science. And while debates about the deeper meaning of quantum mechanics continue, a strange image from the 1930s still lingers as a symbol of the entire mystery. It is the story of Schrödinger's cat, a cat in a sealed box, both alive and dead until someone opens the lid and looks inside. Not because the cat truly exists that way, but because the idea reminds us that at the deepest level of nature, what we assume to be obvious may sometimes be nothing more than a habit of human imagination. As quantum mechanics began to spread through the physics community, a quiet question emerged. What were those equations actually saying about the world? Is the wave function something that truly exists in nature, or merely a mathematical tool for calculating experimental results? And do particles really exist in multiple states at once until we measure them? Ironically, Erwin Schrödinger, the man who wrote the famous equation of quantum mechanics, was also one of the most deeply skeptical about how some scientists interpreted these ideas. He felt there was something unsettling about applying the rules that govern electrons directly to the familiar world around us, so he posed a question that was partly serious and partly ironic. If the strange behavior of quantum mechanics is true at every scale, what would happen if we magnified it to the level of objects we can hold in our hands? Imagine a sealed box. Inside it is a cat. Alongside it are a tiny radioactive atom, a Geiger counter, a vial of poison, and a triggering mechanism. If the atom decays, an event that quantum mechanics says occurs randomly, the Geiger counter detects the signal and triggers the mechanism that shatters the vial of poison. The cat dies. If the atom does not decay, the cat remains alive. But according to the logic of quantum mechanics, before observation, the atom exists in a superposition between decayed and not decayed. And if the entire system is linked together, that would mean the cat in the box must also be in a superposition, both alive and dead at the same time, at least according to certain interpretations of the theory. Of course, Schrödinger never intended to actually put a cat inside such a box. His goal was to highlight the strangeness of applying quantum mechanics to the macroscopic world. The idea of a cat that is both alive and dead sounds more like a joke than science. Yet, it is precisely this absurdity that made the thought experiment such a powerful symbol of quantum mechanics, because it forces us to confront an uncomfortable question. Before observation, what state is a physical system truly in? In the language of quantum mechanics, before measurement, the system exists as a cloud of probabilities, every possibility encoded within the wave function. But the moment a measurement occurs, that cloud collapses. One possibility becomes reality, while the others disappear. What physicists have debated for decades is a seemingly simple question. What exactly counts as an observation? Does it require a conscious observer, or merely a measuring device, or simply any interaction with the environment? These questions have led to different interpretations of quantum mechanics. The Copenhagen interpretation suggests that the wave function represents only what we can know, and measurement simply reveals an outcome. The many worlds interpretation proposes that every possibility actually occurs, each in its own universe. Meanwhile, The decoherence approach argues that interactions with the environment gradually destroy observable superpositions. Although these views differ philosophically, they all agree on one point: quantum systems do not behave like tiny classical objects. The story of the cat, therefore, is not really about a cat. It is about the blurry boundary between observation and reality. In the quantum world, a system may evolve through countless possibilities simultaneously until a measurement forces it to choose. And from these ideas about probability emerges another quantum phenomenon that unsettles our intuition: quantum tunneling. In the familiar world, objects obey very simple rules. If you throw a tennis ball at a wall without enough energy to pass through it, the ball simply bounces back. There is nothing surprising about that. But at the quantum scale, those rules are no longer absolute. A particle can encounter a barrier that it does not have enough energy to cross and still appear on the other side. This phenomenon is called quantum tunneling. Its origin lies in how quantum mechanics describes particles. An electron is not a tiny point moving through space. It is described by a wave function, a spread-out probability wave. When this wave function encounters an energy barrier, it does not stop immediately. Instead, it gradually fades, like an echo weakening as it passes through a wall. And if the barrier is not too thick or too high, a very small portion of the wave function can appear on the other side. That means there is a probability, even if extremely small, that the particle will appear beyond the barrier, not because it breaks through the wall, but because its probability has leaked to the other side. This effect is not just an abstract idea. It plays a crucial role in many physical phenomena. A classic example is alpha radioactive decay. Inside the nucleus of certain atoms, alpha particles are trapped by a very strong energy barrier. According to classical physics, they do not possess enough energy to escape. But thanks to quantum tunneling, their wave function can extend through that barrier. That tiny probability, repeated over time, eventually allows the alpha particle to escape, and this is precisely the mechanism behind radioactive decay. If quantum tunneling did not exist, many processes in the universe simply would not occur. Many radioactive elements would never decay, and nuclear physics as we know it might have stalled from the very beginning. But the most important role of tunneling lies much farther away, in the cores of stars. Inside those enormous cosmic reactors, hydrogen nuclei are squeezed together under immense pressure and temperature. According to classical calculations, even under such extreme conditions, protons still do not possess enough energy to overcome the electrical repulsion between them. If we relied solely on classical physics, nuclear fusion would almost never occur. Yet stars shine for billions of years. The reason lies in quantum tunneling. When nuclei come sufficiently close to one another, their wave functions begin to overlap, and when that happens, there is always a tiny probability that one nucleus can tunnel through the electric barrier and fuse with another. The probability is extremely small, but in a stellar core there are unimaginably many particles, multiplied trillions upon trillions of times. That tiny probability becomes the brilliant source of energy that powers the light of stars and even the explosions of supernovae. Tunneling does not exist only in distant celestial bodies. We have learned to harness it here on Earth. One elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to observe the surfaces of materials at the level of individual atoms. Its principle is remarkably subtle. An extremely sharp probe is brought very close to the surface of a sample, separated by only a few nanometers. At such tiny distances, electrons can tunnel between the probe and the surface of the material. By measuring this tunneling current as the probe scans across the surface, the instrument constructs a detailed map so precise that individual atoms can be distinguished. What is remarkable is that the probe never actually touches the material. The entire image is produced simply through electrons quietly tunneling across empty space. The tunneling effect also appears in many electronic components such as tunnel diodes and quantum dots. And as semiconductor technology continues to shrink transistors down to the nanometer scale, tunneling becomes an unavoidable factor. Energy barriers that were once considered solid in electronic circuits now begin to leak, allowing electrons to slip through places where they are not supposed to go. This creates both challenges and opportunities. It introduces noise in traditional devices, while simultaneously opening the door to new quantum technologies that deliberately exploit the effect. At a deeper level, tunneling reveals something surprising about the nature of reality. In everyday intuition, boundaries seem clear. An object can either pass through something or it cannot. But in the quantum world, barriers are never completely absolute. They are simply very low probabilities, suggestions rather than commands. Yet the strangeness of the quantum world does not end there. Even the vacuum, which we often imagine as completely empty, is not truly silent. In quantum mechanics, what we call nothing is actually a stage filled with invisible fluctuations. Even in the absence of atoms, light, or sound, space itself still vibrates with energy. The uncertainty principle allows energy to fluctuate over extremely short periods of time. These fluctuations give rise to virtual particles, particles that briefly appear and then vanish almost immediately. They cannot be directly observed, but their effects can be measured. One of the clearest demonstrations of this is the Casimir effect. If two extremely thin metal plates are placed very close together in a vacuum, separated by only a few nanometers, classical physics would predict that nothing happens. There is no air and no force. But quantum mechanics reveals something different. The space between the plates allows only certain fluctuations of virtual particles to exist, while outside the plates there is no such restriction. As a result, the pressure from vacuum fluctuations outside becomes greater than the pressure inside, creating a tiny force that pushes the plates together. This force has been measured in precise experiments, as if the vacuum itself were gently pressing the plates toward each other. The concept of vacuum energy also extends to the scale of the cosmos. Some physicists suggest that the energy of empty space may be related to dark energy, the mysterious force causing the expansion of the universe to accelerate. Yet here a major problem appears. When physicists attempt to calculate the total energy of the vacuum using quantum field theory, the result they obtain is about 120 orders of magnitude larger than what observations actually show. This enormous discrepancy is often called the worst prediction in physics. Nevertheless, vacuum fluctuations still play an important role in many experimentally verified phenomena. In quantum electrodynamics, charged particles interact with one another through the continuous exchange of virtual photons. These fluctuations even shift the energy levels of electrons within atoms, a famous effect known as the Lamb shift. Seen in this way, the vacuum is not an empty void. It is more like a quiet background melody upon which all other physical fields, electromagnetic, nuclear, and perhaps even gravitational, vibrate together. Some physicists speculate that within this fluctuating background may lie clues about the deepest structure of the universe, perhaps even about the nature of space-time itself. The only thing we know for certain is this: in the quantum world, even nothing has never truly been silent. In everyday intuition, the vacuum seems like nothing more than a silent emptiness, an empty stage where everything else appears and disappears. But in quantum mechanics, that stage has never truly been quiet. The vacuum is not a passive background. It is alive, structured, and constantly vibrating with hidden possibilities. Even in the coldest regions of the universe, where starlight has faded into distant memory, the quantum vacuum still fluctuates. Particles appear and vanish. Energy fields ripple and settle again like an endless whisper of nature. It reminds us that nothing has never truly been empty. In the quiet spaces between stars, between particles, between moments that seem motionless, the universe is still quietly at work. And it is within this fluctuating world that quantum reality reveals its strange features. Particles do not move along simple straight paths like tiny marbles. They spread out in clouds of probability, exist in superpositions of multiple states at once, become entangled across vast distances, and sometimes even pass through barriers that should be impossible to cross. But perhaps the most mysterious turning point in the quantum story appears when we ask a very human question: what happens when we observe? In the language of quantum mechanics, before measurement, a particle is described by a wave function, a mathematical object containing all the possibilities available to the system. An electron is not just at a single location. It may exist in many places at once. Its spin is not simply up or down. It exists as a combination of both. The wave function resembles a shimmering mist of probabilities filled with countless possibilities. But when a measurement occurs, something very sudden happens. The mist contracts, the possibilities vanish, and only a single outcome remains. The electron appears at a specific position. Its spin chooses a definite direction. This phenomenon is called wave function collapse. What puzzles physicists is that we still do not know exactly what causes this collapse. Is it merely the physical interaction with a measuring device? Is it the exchange of information? Does it require the consciousness of an observer? Or is any interaction with the environment sufficient? This question has led to many different interpretations of quantum mechanics. One of the oldest is the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg. According to this view, the wave function is not a physical object, but simply a tool for predicting probabilities. Before measurement, asking where the particle really is has no meaning. Only when a measurement occurs does a definite result appear. Another, far more radical view is the many worlds interpretation. In this interpretation, the wave function never collapses at all. Every possible outcome happens, but in different branches of the universe. When you measure an electron's spin, the universe splits into multiple versions. In one universe you observe spin up, while in another you observe spin down. There are also objective collapse theories, which propose that the wave function is a physical entity that can spontaneously collapse at random without the need for measurement. And some physicists working within Cubism suggest that the wave function reflects only the beliefs and information of the observer about a quantum system. Amid these interpretations, the concept of decoherence offers part of an explanation. When a quantum system interacts with its surrounding environment, even a few stray photons can be enough. It becomes entangled with that environment. This entanglement causes superposition states to gradually lose their observability. To us, the system appears to have collapsed into a classical state, even though mathematically the quantum evolution continues. And so, more than a century after quantum mechanics was first developed, the question of wave function collapse still lingers like a ghost within the theoretical machinery. The equations work perfectly. Their predictions are astonishingly accurate. Yet what truly happens between measurements remains a mystery. If quantum mechanics has a homeland, the place where these ideas were first seriously debated, it would likely be Copenhagen. It was here that Niels Bohr and his colleagues shaped the famous interpretation that bears the city's name. According to this view, quantum reality before measurement is not a definite state. It is a cloud of probabilities, and measurement does not merely reveal what already existed, it creates the outcome. It is a bold idea that reality, at its deepest level, is not fully determined until we ask a question. And perhaps that is why quantum mechanics continues to leave us both puzzled and amazed, because it suggests that the universe is not a story that has already been written, but rather a piece of music made of possibilities waiting for the moment when we choose to listen. When physicists finally accepted that nature's tiny particles should not be imagined as miniature marbles but rather as waves of probability, many things began to fall into place. The equations suddenly became elegant. Experiments stopped contradicting theory. In this view, the wave function is not an object floating somewhere in space. It is not a map of a particle's true position or true velocity. Instead, it is more like a sophisticated ledger of everything we could possibly know, a catalogue of possibilities rather than a blueprint of reality. From this emerged a central claim of the Copenhagen interpretation. Asking about the state of a system before measurement is a meaningless question. If you ask where an electron is before a measurement occurs, the answer is simply, the question itself has no meaning yet. Where becomes a meaningful concept only after the measurement takes place. Reality is not a curtain we pull back to reveal what was already there. It is more like an image that comes into focus only at the moment we look. Not everyone found this way of thinking comfortable. Albert Einstein was the most famous critic. He believed the universe must exist independently of the observer, an objective reality with a definite structure, whether humans look at it or not. To Einstein, the idea that the state of a system becomes defined only when measured sounded like claiming that the moon exists only when we look up at the sky. Niels Bohr disagreed, but he also avoided proposing a grand metaphysical explanation. Instead, he adopted a more pragmatic stance. Science does not necessarily need to tell us what the world truly is, only what we can meaningfully say about the world based on experiments. This approach left many people both satisfied and uneasy. It worked perfectly in practice. It became the foundation of modern technologies ranging from semiconductors and lasers to quantum computers. Yet it also left a lingering sense that something fundamental was still unresolved. The famous phrase among physicists, "shut up and calculate," partly captures this spirit. Do not worry too much about philosophy, just use the theory to calculate and predict. And indeed, the Copenhagen interpretation does that extremely well. Still, the discomfort remains. If reality only becomes definite when measured, what was the universe like before observers existed? The first galaxies, the first atoms, did they remain in some vague quantum state until someone looked at them? Most physicists believe that human consciousness is not required. In the Copenhagen view, an observation is simply a physical interaction strong enough to force a quantum system into a definite outcome. But even with that explanation, a deeper question remains. Why does nature follow such a strange rule at all? From these concerns, other interpretations began to emerge. One of the boldest appeared in 1957, when physicist Hugh Everett III proposed what later became known as the many worlds interpretation. Imagine tossing a coin. In the familiar world, the coin lands with a single outcome, heads or tails. But in the many worlds picture, the moment the coin lands does not produce just one result. It creates multiple branches of reality. In one branch, the coin is heads. In another branch, it is tails. And in each branch, there exists a version of you witnessing the corresponding outcome. In this interpretation, the wave function never collapses. It simply continues to evolve and branch. When you measure the spin of an electron, the universe does not force the electron to choose. Instead, the entire system, including the electron and the observer, splits into multiple versions corresponding to each possible outcome. One version of you sees the spin pointing up. Another version sees the spin pointing down. Both exist, just in different branches of reality. The idea sounds like science fiction, but what makes it appealing to some physicists is its simplicity. It requires no new assumptions. It does not introduce any special rule for the collapse of the wave function. It simply keeps the mathematics of quantum mechanics exactly as it is and allows it to unfold naturally. Of course, this raises another profound question. If the universe is constantly branching, where do all these branches exist? The many worlds interpretation does not truly answer that. It only says that after branching, the different states become decoherent, meaning they no longer interact or interfere with each other. To us, the other branches become completely invisible. Because of this, many worlds is extremely difficult to test directly. If other universes cannot be observed, how do we know they exist? This remains one of the great debates in the philosophy of physics. But for its supporters, the key question is not, can we see the other universes? But rather, do we need to assume anything beyond the mathematics of quantum theory itself? And there, the debate continues quietly, profoundly, and with no sign of ending. In the debate among the interpretations of quantum mechanics, supporters of the many worlds interpretation often begin with a very simple question. If the Schrödinger equation describes the evolution of a quantum system smoothly and continuously, and if that equation contains no concept of a wave function collapse, then why should we assume that such a collapse exists at all? According to the familiar principle of Occam's razor, that explanations should avoid unnecessary assumptions, this question leads to two different answers. The Copenhagen interpretation keeps the universe conceptually tidy by adding the rule of collapse. Many worlds does the opposite. It keeps the mathematics unchanged and accepts a universe far larger than we once imagined. In this view, the universe does not merely branch occasionally, it branches constantly. Every quantum interaction with multiple possibilities, a photon being emitted, a radioactive decay, a molecular collision, creates new branches of reality. The branching happens endlessly, multiplying exponentially in complete silence. Yet just as we do not feel the earth spinning beneath our feet, we also do not perceive this branching. From the perspective of each observer, only one outcome occurs, as if it were the only path that ever existed. The other realities in many worlds are not parallel worlds in the science fiction sense, where one could step across and meet another version of oneself. After branching, each branch becomes causally separated. No signal can cross that boundary. There is no way to peek into a neighboring branch. Once the separation occurs, it is permanent. In this framework, measurement is not a mysterious moment when reality chooses a result. It is simply a form of entanglement. The observer and the quantum system become linked, and each outcome continues to exist within its own branch. Yet this elegance introduces another question. If every outcome occurs, why do we experience only a single one? Many worlds answers this by redefining the concept of probability. Probability is no longer the chance that an event will happen, but rather the proportion of your future versions that experience each possible outcome. It is a way of thinking that feels very unfamiliar to intuition, but quantum mechanics has never been particularly friendly to intuition. From these reflections on the wave function and branching reality, modern physics takes another step deeper into the structure of the universe. That step is known as quantum field theory. From the perspective of QFT, the universe is not truly built from tiny solid particles. Instead, the foundation of everything is a set of quantum fields spread throughout space. In classical physics, we are already familiar with the concept of a field, for example, the electromagnetic field, a quantity that exists at every point in space and influences charged particles. But once quantum mechanics enters the picture, these fields are no longer quiet. They fluctuate, vibrate, and are never completely still. In the picture offered by QFT, each type of particle corresponds to its own field. An electron is a localized excitation of the electron field. A photon is a vibration of the electromagnetic field. What we call particles are simply small ripples in these fields, quantum excitations that appear and propagate through space. The same electromagnetic field can vibrate in many different ways. One pattern of vibration produces visible light, another produces microwaves, yet another produces X-rays. All of them are simply different modes in which the same field oscillates. This idea transforms how we imagine the universe. Instead of picturing the world as a gigantic Lego structure built from countless tiny bricks, QFT suggests that the universe resembles a symphony. Space is filled with quantum fields, and what we call matter or particles are simply the notes emerging from that cosmic music. This perspective also explains why particle accelerators such as those at CERN can create new particles from energy. When enough energy is concentrated within a tiny region of space, it can excite quantum fields strongly enough to produce new vibrations, in other words, new particles. What appears to be matter emerging from nothing is simply the fields vibrating in new ways. Even antimatter fits naturally into this picture. A positron, the antiparticle of the electron, is simply another kind of excitation of the same electron field, with opposite properties. The fundamental forces of nature can also be understood in this framework. The electromagnetic force can be viewed as the exchange of photons between charged particles. The strong force is carried by gluons in the gluon field, and if gravity is someday fully described within quantum mechanics, it may involve tiny vibrations of a gravitational field particles known as gravitons. What makes this picture particularly elegant is that even empty space is not truly empty. Quantum fields still fluctuate gently, producing vacuum fluctuations, subtle vibrations of the vacuum itself. These fluctuations lead to measurable phenomena such as the Casimir effect, where two metal plates placed very close together in a vacuum are pushed toward each other by differences in the energy of field fluctuations between them. Seen this way, space is no longer an empty backdrop. It becomes a living medium where all physical fields continuously vibrate. And what we call matter, light, and forces are simply different shapes of waves in the vast ocean of quantum fields. At its deepest level, the universe may not be made of objects in the way we usually imagine. When modern physics looks deeply enough into the structure of reality, the picture begins to change. Instead of tiny particles flying through space like little marbles, everything gradually appears as ripples in quantum fields spread throughout the universe. Even mass, the property that makes matter seem heavy and solid, is not necessarily an inherent attribute of particles. In many cases, it emerges from the interaction between particles and the Higgs field, a quantum field that exists throughout space. When scientists confirmed the existence of the Higgs boson in 2012, they also strengthened the idea that mass can arise from the way particles move through this field. A common analogy is to imagine particles swimming through a thick medium. Particles that experience more resistance from the Higgs field appear more massive, while those that interact less move through it more freely. Seen this way, our bodies and everything around us are simply patterns of vibration within a network of quantum fields. The electrons in atoms, the quarks inside protons, the photons carrying light, all are small excitations within their respective fields. Even the thoughts occurring in your brain are nothing more than changing configurations of energy within these fields. And interestingly, these fields do not stop at the boundaries of our bodies. They extend throughout the entire universe, dissolving into a vast ocean of quantum fields. To describe the fundamental components of this world, physicists have developed a theoretical framework known as the Standard Model of Particle Physics. If the universe were like a recipe, the Standard Model would be the list of ingredients. It is not perfect, and it certainly lacks a few mysterious components. But so far, it remains one of the most successful models science has ever created. According to this model, the fundamental constituents of nature fall into three broad groups. First are quarks, the particles that make up protons and neutrons in atomic nuclei. There are 6 types of quarks: up, down, charm, strange, top, and bottom. Among these, the up and down quarks are the most common. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The other quarks are much heavier and usually appear only in extremely high-energy environments, such as particle accelerators or cosmic rays. The second group is leptons. The most familiar member of this group is the electron, the tiny negatively charged particle orbiting atomic nuclei and playing a central role in all chemical reactions. The electron also has 2 heavier relatives, the muon and the tau. Each of these charged particles is paired with a neutral particle called a neutrino. Neutrinos interact extremely weakly with matter. Billions of them pass through our bodies every second without leaving any trace. But a universe containing only matter would not be enough. Particles must also interact with one another, and those interactions are mediated by the third group, bosons. The photon is the boson that carries the electromagnetic force, the force that binds electrons to atoms and allows light to travel through space. The weak force, responsible for certain types of radioactive decay and reactions inside stellar cores, is carried by 3 particles, the W-mice, W-minors, and Z-bosons. The strong force, which binds quarks tightly together inside protons and neutrons, is carried by gluons. Finally, there is the Higgs boson, the manifestation of the Higgs field, the field responsible for giving many particles in the universe their mass. Altogether, the Standard Model describes 12 fundamental matter particles along with the force-carrying bosons associated with them. What is remarkable is how accurately this model has predicted experimental results over many decades. From collisions inside particle accelerators to atomic decay processes, measurements consistently match theoretical predictions with astonishing precision. Yet the standard model is still not the complete picture of the universe. It does not include gravity, the force Einstein described through general relativity. It also cannot explain dark matter, the invisible substance that seems to make up most of the mass of galaxies, or dark energy, the mysterious phenomenon causing the universe's expansion to accelerate. In other words, the standard model describes only about 5% of the universe's contents. But that 5% includes all familiar matter, every atom, every chemical reaction, every living organism. Within this intricate web of interactions, one theory stands out for its extraordinary precision: quantum electrodynamics, or QED. This theory describes how light and electrically charged particles interact. At the quantum level, these interactions can be understood as a kind of dance between electrons and photons. Charged particles exchange photons with one another, and those exchanges produce the electromagnetic force. Every beam of light, every spark of electricity, every attraction or repulsion between charges is part of that dance. What makes QED remarkable is its precision. The predictions of this theory match experimental results to many decimal places so precisely that physicists sometimes pause simply to marvel at it. When we step back and look at the whole picture, the universe no longer resembles a machine made of solid gears. Instead, it looks more like a symphony of quantum fields, where every particle is merely a fleeting ripple, and within that symphony, matter, light, and forces are simply different ways in which the fields of nature vibrate through space and time. One of the things that makes quantum electrodynamics, QED, almost legendary in physics, is its extraordinary precision. Even though the theory must account for countless possible interactions and incredibly complex quantum probabilities, the final numbers it produces match experimental results with astonishing accuracy. Its precision can reach better than 1 part in a billion. Imagine measuring the width of the entire North American continent with an error no greater than the thickness of a single human hair. That is the level of accuracy achieved by QED. But before reaching that elegance, physicists had to confront a deeply troubling problem. Since the early 20th century, scientists had known that electrons interact with the electromagnetic field. When an electron accelerates, it emits light. When it absorbs light, its energy level changes. However, when physicists attempted to calculate these interactions precisely at the quantum level, the mathematics quickly became chaotic. The equations began producing infinities nonsensical results such as infinite energy. This problem was eventually resolved through the work of Richard Feynman, along with Julian Schwinger and Shinichiro Tomonaga. They developed methods that allowed the theory to function without being destroyed by these infinities. But Feynman contributed something even more remarkable. He turned complicated calculations into pictures. He introduced what are now known as Feynman diagrams. In these diagrams, particles are represented by straight or curved lines. Time is usually drawn in one direction, and interactions occur at points where the lines meet. An electron might enter the diagram, emit a photon, and continue on its path. That photon might travel to another electron or even loop back and interact with the original electron itself. Each diagram corresponds to a mathematical expression, and the remarkable feature of QED is this: to find the final result, you do not calculate just one path. You must add together all possible paths. Every way an interaction could occur, no matter how unlikely, contributes to the final answer. Among these possibilities are some very strange scenarios. A photon might temporarily transform into an electron-positron pair, and then the pair annihilates again to produce another photon before the interaction continues. These intermediate entities are called virtual particles. They cannot be observed directly as real particles, yet their influence appears clearly in the final outcome of experiments. In this sense, QED is almost like a poem written in mathematics. It does not calculate only what actually happens, it calculates everything that could happen. Every loop, every branch, every imagined path is included in the calculation. And when all these possibilities are summed together, the result agrees with experiments with astonishing accuracy. One of the most famous triumphs of QED is its prediction of the electron's anomalous magnetic moment. The electron behaves like an extremely tiny magnet. Classical physics can predict the strength of this magnetic field approximately, but quantum effects modify it slightly. QED calculates this tiny correction, and the result matches experimental measurements to more than 10 decimal places. QED also successfully describes many other phenomena: Compton scattering, where a photon collides with an electron and changes direction; Bremsstrahlung, where a particle emits radiation as it slows down; and pair production, where light can transform into matter and antimatter. Processes that sound almost magical are, in fact, natural consequences of the rules of QED. QED does not stand alone. It is the quantum field theory of electromagnetism, and it also became the template for other theories. The strong force is described by quantum chromodynamics (QCD), while the weak force forms part of the electroweak theory. But QED was the first theory to reach such extraordinary precision, and for that reason, it became the benchmark for the entire field of particle physics. Interestingly, according to Feynman himself, the core rules of QED could almost be written on the back of a napkin. The central idea is surprisingly simple. A particle does not travel along a single path from point A to point B. Instead, it travels along every possible path, each carrying a probability amplitude. Add together all those amplitudes, then square the result, and you obtain the actual probability of the event. From this perspective, when an electron moves, it does not simply travel straight through space. It explores every imaginable path, looping around obstacles, curving through unseen routes, even doubling back on itself all at once. And from the combination of those countless paths, the reality we observe gradually emerges. In the world of quantum electrodynamics, QED, the universe seems to be performing an immense calculation. Every interaction between light and matter does not follow a single path, but instead emerges from the combination of countless possibilities existing at once. This theory allows physicists to glimpse that process the way nature adds up all possible paths before producing a result we can measure. What is astonishing is that, despite accounting for countless imaginary interactions and almost infinite possibilities, the predictions of QED still match experiments with remarkable accuracy. Its precision reaches the level of 1 part in a billion. In the history of science, few theories have ever been tested so thoroughly and confirmed so precisely. Of course, QED is not the final answer to every question. It does not include gravity, nor does it explain dark matter. But within its domain describing how light and electrically charged particles interact, QED is nearly unmatched. Richard Feynman, one of the architects of the theory, himself acknowledged how extraordinary it was. Yet he also reminded us that nature always holds further surprises. QED may be the best theory we currently have, but it may not be the best theory we will ever discover. Still, for now it stands almost like a masterpiece. A theory born from tangled equations and philosophical debates eventually became a clear description of the quantum rhythm of the universe, where light and matter whisper to each other through laws precise down to many decimal places. Those laws are everywhere, in the light of distant stars, in the glowing screen of the phone in front of you, in the small lamp beside your bed. Every beam of light, every reflection, is part of the dance between electrons and photons, a dance occurring billions of times each second with extraordinary precision. And from the strange rules of this quantum world, a new idea eventually emerged: quantum computers. If a classical computer is like a meticulous librarian reading one page at a time in careful sequence, then a quantum computer is more like a strange poet who can read all the books at once, their whispers overlapping, and somehow discover the answer. To understand this, we first need to meet a new concept: the qubit. In ordinary computers, all information is stored using bits. A bit has only 2 possible states: 0 or 1. Every program, video, image, or calculation is ultimately built from billions of these bits. But a qubit is different. Thanks to superposition, a qubit can exist in a combination of 0 and 1 at the same time. A helpful image is a spinning coin. While it spins in the air, it is neither heads nor tails. It contains the potential for both. When multiple qubits are combined, the number of possible states grows extremely quickly. 2 qubits can represent 4 states at once. 3 qubits represent 8. 20 qubits already represent over 1 million possibilities simultaneously. With enough qubits, a quantum system can explore an enormous number of possibilities at once. But this does not mean a quantum computer simply tries every answer simultaneously. The secret lies in how quantum algorithms manipulate probabilities, amplifying the likelihood of the correct answer so that when the system is measured, the right result appears most often. Besides superposition, quantum computers also exploit another phenomenon: entanglement. When qubits become entangled, their states become linked. A change in one qubit is connected to the state of another, even when they are far apart. These correlations allow quantum systems to perform calculations that classical bits cannot efficiently simulate. Because of these properties, quantum computers have the potential to solve certain extremely difficult problems, such as simulating molecular behavior in chemistry, optimizing complex systems, or analyzing enormous numbers in cryptography. However, the reality today is still quite modest. Quantum computers are not devices that will replace your laptop anytime soon. They are highly specialized machines, and building them is extraordinarily difficult. Qubits are extremely fragile. They can be disrupted by tiny vibrations, temperature fluctuations, or even weak magnetic fields. To keep qubits stable, many systems must operate at temperatures close to absolute zero, colder even than deep space. Error correction is also far more complicated than in classical computing. In quantum systems, you cannot simply copy the state of a qubit to check it, because the no-cloning theorem of quantum mechanics forbids that. Instead, researchers must use many physical qubits to protect a single logical qubit, like surrounding a delicate signal with multiple layers of protection. Even so, progress has been rapid. Laboratories and technology companies have already built systems with dozens or even hundreds of qubits. Some experiments have demonstrated what is called quantum supremacy, where a quantum computer performs a task that classical computers would struggle to complete within a reasonable time. What is fascinating is that the phenomena that once puzzled physicists, superposition, entanglement, and measurement collapse, are now becoming tools. Ideas that once appeared as philosophical paradoxes are gradually turning into technologies. And perhaps that is the most beautiful part of the quantum story. The strangeness of nature is not merely something that confuses us. Sometimes, that very strangeness opens entirely new ways to understand and explore the universe. In the world of quantum computing, we are not trying to conquer nature's strange rules by fighting against them. Instead, we learn to move with them like a sailor harnessing a strong wind to fill the sails and head out to sea. Quantum computers are not simply a new kind of computer. They force us to rethink the very idea of computation itself, a place where the boundary between certainty and probability becomes softer, where solutions emerge not from step-by-step procedures, but from the subtle coordination of countless possibilities. And although we do not yet know where this technological journey will lead, simply stepping onto this path has already changed the way we think about machine intelligence and about our own capabilities. In quantum physics, we have grown accustomed to strange phenomena. Particles can tunnel through barriers that seem impossible to cross, exist in multiple states at once, or become entangled in pairs that respond to each other even when separated by thousands of kilometers. But there was once a place where such effects were thought impossible. That place was biology. Biology is a noisy and chaotic world. Molecules constantly collide, temperatures fluctuate, and energy is always in motion. Meanwhile, quantum effects are famously fragile. Even a little heat or disturbance can destroy them. For this reason, in laboratories, scientists often cool quantum systems close to absolute zero and isolate them in vacuum environments. And yet, it seems that life may have found its own ways of using quantum phenomena. Let us begin with a small bird, the European robin. These birds can migrate thousands of kilometers with astonishing accuracy. For many years, scientists believed they possessed some kind of biological compass, but the mechanism behind it remained a mystery. Then a bold idea appeared. Quantum entanglement might play a role in their navigation. The hypothesis suggests that within the bird's eyes there is a protein called cryptochrome. When light strikes this molecule, it excites a pair of electrons. These two electrons may become entangled with each other. Their spin states then interact with the Earth's magnetic field, subtly altering a chemical reaction within the molecule. That change depends on the direction the bird is facing, creating a signal that helps it detect orientation. At first, this idea seemed almost too bold. Quantum entanglement is extremely delicate. Could it really survive inside the chaotic environment of living cells? Surprisingly, some early experiments suggest that it might. Although there is still no final conclusion, increasing evidence indicates that birds may indeed use a quantum process to sense magnetic fields. If that turns out to be true, then nature has achieved something that human engineers still struggle to accomplish: maintaining quantum information in warm, complex environments. From migrating birds, we move to a greener and quieter world: plants. The process of photosynthesis, in which plants convert light into chemical energy, sounds straightforward. Light is absorbed by molecules such as chlorophyll, and that energy is then transferred to a reaction center where it is stored. But the question is, how does that energy travel? From a classical perspective, energy would hop randomly from one molecule to another until it eventually reaches its destination. But that method would be relatively slow and inefficient. Experiments suggest something more subtle is happening. Energy appears to explore many possible pathways simultaneously, spreading like a wave across a network of molecules before selecting the most efficient route. This phenomenon can be explained by quantum coherence, a state that allows the system to maintain a superposition of multiple possibilities for a very short time. Imagine dropping a marble into a maze. Instead of traveling through one corridor at a time, it spreads like a wave, sensing every path at once, and then naturally concentrates along the shortest route. Some scientists believe photosynthetic complexes in plants may work in a similar way. What makes this remarkable is that the environment inside plant cells is warm and full of noise. Yet coherence still survives for an extremely brief moment, only a few picoseconds, but long enough to influence the efficiency of energy transfer. All of this leads to a fascinating question. Has evolution learned to exploit quantum mechanics? Nature has had billions of years to experiment. If any organism happened to gain even a small advantage from quantum effects, that advantage might improve its chances of survival. And there is another biological mystery that might involve quantum physics: the sense of smell. The traditional explanation suggests that we detect odors because molecules fit into receptors in the nose like keys fitting into locks. But this explanation is not perfect. Some molecules with very similar shapes produce very different smells. Conversely, molecules with quite different structures sometimes smell almost identical. Another hypothesis, known as the vibrational theory of olfaction, suggests that our noses may detect the vibrational frequencies of molecules. When a molecule binds to a receptor, an electron in the receptor might tunnel through the molecule. The probability of tunneling depends on the vibrational frequency of that molecule. If this is true, then smelling could directly involve quantum tunneling, the same phenomenon that allows particles to pass through barriers in nuclear reactions inside stars. Some experiments suggest that humans and even fruit flies can distinguish between molecules that differ only in their vibrational frequencies. Although the evidence is not yet conclusive, it is intriguing enough to keep scientists investigating further. The field of quantum biology is still very young. It is built from bold hypotheses, early experiments, and many unanswered questions. Yet that very newness is what makes it so exciting, because it reminds us that the strange rules of quantum mechanics may not exist only inside laboratories. They may be quietly operating within the living world around us, in the wings of migrating birds, in the leaves absorbing sunlight, and perhaps even within our own breath and senses. At the deepest level of nature, the laws of quantum mechanics do not exist only in laboratories or within abstract equations. They seem to weave their way into life itself. The same principles once used to describe electrons in empty space appear in the wings of migrating birds, in the leaf absorbing sunlight, even in the breath you just took. Nature does not divide the world into physics and biology. Quantum effects are not confined to some microscopic corner of the universe. They are woven into the very structure of life. That realization invites a certain humility. The mathematical tools used to describe fundamental particles also help explain phenomena that seem entirely ordinary, the sound of birds singing in the morning, or the shimmer of light on a leaf. Perhaps, over billions of years of evolution, life has quietly learned to take advantage of the strangest rules of the universe without ever needing to explain them to us. But then a natural question arises. If the quantum world is filled with superpositions and uncertain probabilities, why doesn't the world around us look like that? Why doesn't the cup of coffee on your table exist in multiple places at once? Why isn't the loaf of bread in the refrigerator in a state of maybe there, maybe not, until you open the door? The answer lies in a quiet but profoundly important process: decoherence. In the quantum world, a particle such as an electron can exist in superposition, a combination of many possibilities at once. If the electron were perfectly isolated in empty space, that delicate state might persist for quite a long time. But in the real world, perfect isolation almost never occurs. Air, light, heat, surrounding molecules, background radiation, all of these constantly interact with a quantum system. Each interaction gradually causes the system to lose coherence, meaning its ability to maintain clear superposition states. The delicate interference patterns begin to fade. This process is what we call decoherence. Importantly, decoherence is not a sudden collapse. It is more like a slow erosion. As a quantum system interacts with its environment, it becomes entangled with countless surrounding particles. From that moment on, the system no longer behaves like a pure probability wave. It begins to resemble an ordinary object, stable and with a definite position. A simple way to imagine this is to think of quantum systems as preferring privacy. But the universe never leaves them alone. Air molecules, photons, thermal vibrations, all act like countless tiny observers, constantly disturbing the quantum state. For extremely small systems, like atoms, we can sometimes isolate them well enough for quantum behavior to survive. But for larger objects, decoherence happens extraordinarily fast, sometimes within a trillionth of a second. That is why you never walk into a room and see your shoes existing as a fuzzy cloud of probability. Environmental interactions have already forced their state to become definite long before you arrive. In a sense, decoherence does not destroy superposition, it hides it. The possibilities still exist in principle, but they become entangled with so many environmental factors that they can no longer be observed or reversed. The result is the emergence of the classical world. This is the bridge between two worlds. Classical physics, the kind we use to build bridges, launch rockets, or cook dinner, still works extremely well. Yet beneath that stable surface, the universe continues to vibrate according to quantum rules. A helpful analogy is to imagine walking across the frozen surface of a lake. Beneath the ice lies liquid water moving, fluid, like the quantum world. The ice above is solid and reliable, like the classical world we experience. Decoherence is the process that freezes the surface of the lake. It does not eliminate the water beneath. It simply prevents us from directly touching it. This phenomenon also has very practical consequences. Quantum computers must constantly battle decoherence. Even a tiny vibration, or a small change in temperature, can destroy the delicate quantum state of a qubit. That is why many quantum systems must operate in extremely cold and carefully isolated environments. Even so, decoherence does not solve every mystery of quantum mechanics. It helps explain why we do not observe quantum interference in the macroscopic world, but it does not answer the deeper question, why a specific outcome appears in a measurement. What it does tell us, however, is something important. The classical world is not separate from the quantum world. It is simply the version of reality that has been filtered through countless interactions with the environment. And just when it seems that quantum physics could not become any stranger, physicists discovered experiments that challenge even our notions of time and causality. Consider again the famous double-slit experiment. When particles such as photons pass through two slits without being observed, they produce an interference pattern, as if each particle passed through both slits at once. But if a detector is placed to determine which slit the particle travels through, the interference pattern disappears. The particle behaves like a tiny bullet. That alone is strange enough. But in the delayed choice experiment, physicist John Archibald Wheeler proposed an even more subtle variation. You allow the particle to pass through the slits first, and only afterward decide whether or not to measure which path it took. The pattern on the screen still matches the choice you made, even though that choice was made after the particle had already passed through the slits. If you choose to measure the path, the particle behaves like a particle. If you do not measure it, the particle produces interference like a wave. It almost seems as though the particle somehow knows the future choice and adjusts its behavior in the past. At least, that is how it appears. The delayed choice experiment suggests something profoundly strange. In the quantum world, reality may not be fully determined until a measurement occurs. Until that moment, it exists as a collection of possibilities, a story not yet fully written. And only when we force the universe to answer does the story finally choose an ending. At the quantum level, the strange phenomena do not occur only in space, they also seem to reach into time itself. When physicists studied experiments like the double-slit experiment more deeply, they realized that observation does not merely determine the final result. It seems to influence how the story unfolded before that moment. From this idea, scientists created an even more daring variation, the quantum eraser experiment. In this version, particles are marked so that researchers can determine which slit they pass through. When which path information exists, the interference pattern disappears. The particles behave like tiny bullets. But then, through a subtle technique, the researchers erase the information about the particle's path after the particles have already been detected. And something remarkable happens. The interference pattern returns. It appears as though the particles behave like waves again, as if the information about their path had never existed. This leads to a deeply puzzling idea. Reality may not be completely settled until all relevant information about the system has been determined. In other words, not only the moment of measurement matters, the way we process information about that measurement can also affect what we observe. The idea resembles a time-extended version of Schrödinger's cat. Not only is the cat both alive and dead until the box is opened, but the state might even depend on decisions made after the box has already been opened. So what is really happening? One intriguing explanation suggests that information itself may be the most fundamental ingredient of reality. Outcomes are not fixed until the questions that could reveal them are actually asked. Before that moment, possibilities coexist together within a hazy region of probability. This does not mean we can travel through time or change the past. At large scales, experiments still obey ordinary causality, but they hint that, at deeper levels, time and cause may not be as simple or as strictly linear as we once believed. Some physicists describe these phenomena using the language of correlations and entanglement, rather than cause and effect. A particle does not know a future decision. Instead, the entire experiment, from the source of the particles to the detectors, and even the way the data is analyzed, forms a single, interconnected system whose final configuration determines the observed pattern. Others imagine the universe as a block universe, where all moments in time exist simultaneously, like frames of a film. In that picture, your choice does not travel backward into the past. It was simply always part of the entire quantum story. And of course, some physicists simply shrug and say, just calculate. The important point is this: the universe is under no obligation to obey our intuitive ideas about time, causality, or measurement. Our intuition evolved in the macroscopic world, a world of rocks, tables, cups of coffee, and cats that are very clearly either alive or dead. But deep beneath the quantum mist, the rules appear far more flexible, more non-linear, and far stranger. Experiments like delayed choice and quantum eraser do not break physics. On the contrary, they reveal its depth. They show that the quantum world is not simply a miniature version of our everyday world. It is a fundamentally different reality, operating according to its own logic. And if time sometimes seems to play tricks on us, then at the quantum level, perhaps it really is. If you continue to zoom deeper into the structure of the universe beyond galaxies, molecules, and atoms, you eventually arrive at a realm where certainty begins to dissolve. There, events are no longer predetermined. They can only be described in terms of probabilities. Particles have no definite position until you observe them, and even then, the result is only one among many possibilities. That is the quantum universe. A universe where randomness does not merely exist, it may be one of the fundamental principles of nature itself. This idea deeply troubled Albert Einstein. He famously remarked, "God does not play dice with the universe." Yet quantum mechanics seems to suggest the opposite. In classical physics, if you knew the exact position and velocity of every particle, you could predict the future perfectly. The universe would behave like a giant machine. But quantum mechanics replaces that picture with the wave function, a description of all possible outcomes. When a measurement occurs, the wave function collapses into a specific result. But which result appears is not predetermined. It is genuinely random. Not because we lack information, not because our instruments are imperfect, but because the very structure of reality allows it. Some interpretations, such as many worlds, try to avoid this randomness by proposing that every outcome occurs in different universes. Yet, from the perspective of any single observer, the result still cannot be predicted in advance. This opens profound philosophical questions. If randomness exists at the foundation of the universe, what does that mean for causality? For free will? At first, a universe without a predetermined script might seem unsettling, but randomness does not mean chaos. Quantum mechanics remains extremely precise when predicting the probabilities of events. It is like rolling hundreds of dice. Each individual roll is random, yet the overall distribution follows very stable statistical laws. Because of this, when enormous numbers of particles are involved, the classical world emerges. That is why your cup of coffee does not suddenly tunnel through the table, even though individual particles, in principle, could. From another perspective, this randomness may actually be the source of the universe's richness and diversity. In biology, small changes in genes' random mutations can lead to entirely new evolutionary paths. If everything were absolutely predetermined, there might be no leaves, no leopards, and no humans pondering the universe. In the quantum world, randomness is not a flaw in nature. It is the engine of possibility. It allows new outcomes to emerge, eventually creating the complex structures we see today. And that means the universe is not completely locked into a rigid chain of deterministic events. It is more like a vast deck of cards, where each card carries its own probability, and every draw writes the story of reality in a slightly different way. In the quantum world, even when particles are prepared in exactly the same way, their outcomes can still be different. That tiny difference, a whisper of uncertainty, keeps the universe from ever becoming dull. Perhaps the universe really is rolling the dice, but not chaotically. It is a game so subtle that from those fragile probabilities arise galaxies, atoms, thoughts, and even time. Instead of seeing randomness as a flaw in the machinery of the universe, we might view it as a very soft background music, a vibration of possibility that is always present in the structure of reality. If quantum mechanics was simply a collection of equations, no matter how strange or beautiful they might be, it would still stand as one of humanity's greatest intellectual achievements. But what makes it even more remarkable is that it does not only speak about particles and probabilities. It invites us to think about deeper questions. What does it mean to know? And what does it mean to exist? In everyday intuition, We tend to believe that reality is something solid, existing independently out there, whether we observe it or not. But the quantum world suggests something different. At the smallest scales, reality is not fixed. It resembles a set of possibilities waiting to be shaped. A particle in a superposition is not undecided, but rather carries all possible states at once. It is more like a blurred cloud of probability than a single definite point. And when we measure it, that blur collapses into one single outcome, as if the universe gently exhales and chooses a story. That idea leads to a rather strange question. If observation plays such an important role, are we truly separate from the universe? Or are we ourselves part of that immense, entangled dance? For physicists, these are technical questions, but for many people, they carry philosophical undertones. Still, quantum mechanics is not a shortcut to enlightenment. It does not provide simple answers. What it offers instead is something more valuable: humility. It reminds us that our everyday intuition about space, time, matter, and causality is not the final word. The familiar world we experience is only one version of reality, filtered through our senses, through evolution, and through habits of perception. In that sense, quantum mechanics is not only physics. It is like a mirror reflecting the limits of our understanding and showing just how strange the universe truly is. Think of Schrödinger's cat not as a cat trapped in a paradox, but as a metaphor for life itself. We often live in states of unresolved possibilities, waiting for medical results, waiting for a response from a new job, or simply wondering whether it will rain tomorrow. In those moments, hope and anxiety coexist like a kind of emotional superposition. Only when time passes or a decision is made does the wave function of life collapse into a concrete outcome. Perhaps that is the quiet beauty of quantum mechanics. It does not say that the world is meaningless or impossible to understand. It simply reminds us that the universe has no obligation to be obvious. If certainty is not guaranteed, then possibility is not limited. If reality is not fixed until it is observed, then potential is always there, shimmering somewhere just beyond our sight. Even the word quantum carries a certain poetry. It comes from the Latin quantus, how much energy, how much light, how much change is allowed to occur. Yet it also reminds us that the world has its smallest jumps, its discrete units of transformation. In the vast chaos of the universe, there are still tiny thresholds that everything must cross. Not all change is smooth. Some happens in leaps, like when you dream. You do not step atom by atom into a dream. You jump straight into another world, and when you wake, you carry with you the feeling that reality might be larger than you thought. Quantum mechanics can feel like that, like waking from a dream and realizing the world is stranger, wider, and more beautiful than you once imagined. Of course, that sometimes makes people uneasy. We like certainty. We like clear causes and clear effects. But perhaps certainty is also a little overrated. Perhaps sometimes we can accept living with unanswered questions, to wander through a forest of probabilities without needing to know which tree is real. Perhaps it is in that space between understanding and not understanding that wonder truly lives. Richard Feynman once said, "I think I can safely say that nobody really understands quantum mechanics." He said it half-jokingly. Even those who work with the equations every day admit that quantum mechanics is not something you understand in the ordinary sense. You can only accept it the way you accept a poem or a dream. It works. It is precise. It is testable. Yet it refuses to be confined within familiar logic. And perhaps that makes it more honest, because the universe was never obligated to be simple. It only needs to exist. So, as we gently drift through these quantum ideas, perhaps the greatest lesson is not about particles or probabilities, but about perspective. To see uncertainty not as a flaw, but as a feature of reality. A reminder that we are part of a universe still unfolding, still choosing, still vibrating with possibility. A place where even the vacuum is not truly empty. Where time can bend, light sometimes forgets how it is supposed to behave, and reality itself sometimes feels as though it might be dreaming. Thank you for listening. Whether you are still awake, slowly drifting towards sleep, or already halfway inside a dream, we have traveled a long path together, through tiny slits in cardboard, through cats in boxes, through vibrating quantum fields, and experiments that make time itself feel confused. Along that journey, we have not only seen the strangeness of the quantum world, but also its quiet beauty. At first glance, it may all seem too strange to believe. A universe where a particle is not truly anything until it is observed, where cause and effect sometimes blur at the edges, where a particle can be here and somewhere else. Yet quantum mechanics keeps reminding us of one thing: the familiar world we touch every day is only the surface. Beneath it lies a softer world, stranger, but also more flexible. A world built not from certainty, but from shimmering possibilities. And we are not outside that world. We are made from those very quantum fields, from the atoms in our fingertips, the light reflected in our eyes, to the oxygen in our lungs. You do not just live in the universe, you are part of it. And perhaps that is a little poetic too. At the beginning, I asked where you were listening from. Perhaps you are lying beneath a warm blanket, staring at the ceiling, or perhaps you are somewhere far from sleep. Wherever you are, I hope this journey offered you a moment of something a little quiet, a little wonder, or simply a pause. Because when we look into the heart of matter and ask, what is real? Quantum mechanics does not give us a final answer. It simply hands us a mirror that is always changing. And sometimes, the question can be just as beautiful as the answer. From Sleepy Scientist wishing you a peaceful night.